about common source amplifier with diode connected load. So what is in the diode connected load? We're looking from the any terminal, the drain terminal or source terminal, the impedance is same 1 by Gm. Okay, so using the diode connected load, we have taken the NMOS connected load and PMOS diode connected load. We have found the output gain, or we have found the gain. So any doubt in last class? Shall we proceed? Okay. So today's class will start from the current source load, common source stage with current source load. Okay. Fine. So before that thing, what is the gain formula for resistive load? I don't know how to close this thing. Okay. So what is the gain formula for the resistive load? Anyone can answer?
Minus Gm RD.
RD. Okay. Let's assume RD parallel with R0.
R0.
Okay. If RD very smaller than R0 or R0 is much higher, I can approximate minus Gm into RD. Now I am fixing some input state, some overdrive I am fixing. Let's take overdrive is fixed value, minimum overdrive. Let's take 0.1. If overdrive is fixed, what is Gm? What is the relation between overdrive and Gm? What is the formula? Current also fixed. So Gm by ID equal to 2 by overdrive. So overdrive is fixed. So current we already know that is also fixed value. So Gm also fixed because overdrive is fixed, Gm is fixed. Fine. So I want to increase the gain. You know Gm is fixed now. So how can I increase the gain now? Only increasing the RD. Am I right? So gain can be increased by increasing the RD. Fine. So I want to increase the RD. So what will happen if I increase the RD? Okay, if I increase the RD, what will be your problem? Anyone can answer? If I increase the RD here, okay, gain will increase, but as per a large signal perspective, increase the RD. What is V out? VDD minus ID RD. Okay, increase the RD increases the gain. Okay, RD increases. Like the first thing is gain increases. So, but what will be the problem? Anyone can answer by looking on this formula. What will happen? Increasing the RD. Output swing increases or decreases?
Output decreases.
Output swing because we are decreasing the output DC level. What is the swing? With respect to the DC level, how much swing? So this is a DC level. So this is a swing. Okay, so DC level is decreasing. But so DC level decreasing, definitely swing will reduce. Okay, so RD increases. The drawback is output swing reduces. Right. So even though I increase the RD, I cannot, but we can get more gain. We can get more gain, but cost of decreased output swing. Is it understandable? Yes. Any doubts?
Yes.
Okay. So, but I want more gain. So what can I do? Instead of RD, let me. I'm sorry. Let me V in. Okay. I am replacing RD with some current source. So anyone can say what is a gain now? So replaced by current source. So what will be gain now? You know the gain formula here. Okay, so what will be the gain now? Okay, in current showcase, let me write here. Okay, to increase gain, I am replacing RD by current source. So what is the gain here? AV equal to minus GM into RD parallel with R0. Okay, so now I am replacing by current source V0. So what will be the gain now? What is RD here? What is current source output impedance?
Infinite.
Infinite. RD equal to infinite. If RD equal to infinite, what will be the gain? Anything parallel with infinite. What will be the answer?
Minus GM R0.
Minus GM R0. Fine. Good. So minus GM R0. Fine. So you can see how we will get minus GM R0. Let me draw the. Okay. So let me draw the small signal equivalent here. Okay. I'm sorry. I'll move this blank shade here. Okay, so here minus GM R0. So before thing, let me draw the small signal circuit. Okay. So here V in. Okay. Okay. V in. Okay. BJS is V in. Okay. BJS is V in. So GM V in. R0 is there, drain to source R0. RD is infinite. Okay, current source means RD is infinite. So there is no load resistance. So now you can see what is V0? This is V0. So V0 is minus GM V in, current flows to this R0, that is V0. So AV equal to V0 by V in equal to minus GM R0. Is it understandable? Yes?
Yes, sir.
Yes? No responses?
Yes, sir.
Is it fine?
Yes, sir.
Yeah. So now, okay, so what is the GM? GM is a parameter of transistor M1. Let's take M1. What about R0? R0 is a parameter of M1. Whether is there any parameter due to the load? Is there any parameter? This is the load. Load current source. Is there any parameter? So let's take current source is IB, bias current IB. Is there any related parameter in this gain? Yes or no? Is it there or not?
No, sir.
Huh?
No, sir.
Okay, that means this parameter only due to the transistor. So this parameter due to transistor, this gain is due to the only transistor. So this is called the intrinsic gain. That means it is a maximum gain can able to given by the single transistor such that current the load is ideal current source. That means ideal current source means infinite, RD is infinite. So ideal current source means, okay, so let me write ideal current source load, that means that is RD equal to infinite. Fine. So if you apply ideal current source, we can able to get maximum gain from the transistor. So what is the purpose we are using transistor? To get a gain. So how much maximum gain we can get? Minus GMR0, because RD is infinite maximum. So this is the maximum gain from the transistor. It's called as intrinsic gain of the transistor. This is the maximum gain we can get. Fine. So now we can say minus GM into R0. So how will we get increased gain here? GM into R0. So R0 we want more R0. So you know R0 is proportional to L. Okay, so when you increase the L, we can get more intrinsic gain. So increases with L. Intrinsic gain increases with L. Okay, it decreases with ID. So let's substitute the GM expression here. It will proportional to root ID. R naught equal to 1 by lambda ID. So now you can see GM R naught proportional to 1 by root ID. It decreases with the ID. So this is not important. The only important thing is intrinsic gain increases with L. This is only much important. You don't worry about this. Fine. So now you understand common source amplifier with current source, ideal current source. Okay. So now I want to replace ideal current source with the practical thing. Fine. I want to replace ideal thing. We using the practical current source. So how can I implement this current source? Current coming from the supply. How can I implement this thing? What can I put here? Yes. What can I put here? I already discussed many times. Current coming from the supply. We need to use PMOS current source or NMOS current source?
PMOS.
PMOS. B in, B naught. Apply some bias potential. But so this is a PMOS current source. Okay, because coming from the supply. Similarly, NMOS means it sinks towards ground. Okay, so now we'll come here. So now we'll put ideal current source by practical current source. Implementing. I'm trying to implement the current source in load because current source already understood. Current source will give more load resistance. Fine. So what is the load resistance now of PMOS? Okay, so let me I'm replaying here. So this is a okay. So let me ideal current source means looking from here, impedance is RD is infinite. Now I'm putting PMOS. So what is RD now? Yes. Bias voltage is a fixed value. So what is RD? Yes. Any response? Let me draw a small signal circuit. VB, okay, grounded. Whether GM VGS will come? Here also it is grounded. Whether GM VGS, this current source will come? What is VGS here?
Zero.
Huh? 0. VGS 0, GM VGS won't be there. So what term will be there? Yes, what will be there?
Open circuit.
Huh?
Open circuit.
Can you speak louder?
Sir, open circuit.
No, you forgot one more effect. When I consider channel and modulation, what will be there?
R naught.
R naught will
R
be there.
naught.
So what will be the RD now?
R naught.
R naught. R naught is higher, not smaller value. Right? So you can see here. I'm sorry, one second I'm doing it. So you can see here. Okay, so R naught will be there. So what will be the gain will be now? Okay, here R naught 2, here R naught 1. So you can see looking from here R naught 2, looking from here. I'm sorry. R naught 1. So equivalent RD is R naught 1 parallel with R naught 2. So minus GM1 R naught 1 parallel with R naught 2. Is it fine? Okay, so now
Sir.
with the practical current source, the gain will become minus GM1 R naught 1 parallel to R naught 2. It is significantly higher than the RD. R naught 1 parallel to R naught 2 is significantly higher than the RD. Any doubts here? Okay, so you can see there's some problems here. This gain expression will come here. Fine. So, and one more thing here, whenever you are connecting PMOS transistor drain node and the NMOS transistor drain node. Okay, you can see both drains are connected here. Okay, this voltage at the drain node, it is not fixed. Okay, so both will try to give the different current values. Okay, so it will, okay, so it depends on the thing, which current is much higher. So according to the current, this node will be fixed to that particular voltage. Okay, so it is always not recommended to connect to things to establish that node voltage. We will use common mode feedback circuit. Okay, that thing will study in op amp. Okay, so always remember when you connect both NMOS and PMOS drain nodes together, that potential is not constant thing. It will vary, depends on the current value in NMOS and PMOS. So it will randomly fix to some value. Okay, to fix to the drain voltage to a known voltage, we have to use common mode feedback. Okay, but in common source amplifier, we are going to do next lab. We are going to do this experiment only. I will tell you how to fix this node voltage. I will tell you in the lab without using the common mode feedback. I will tell some simple idea because we need to simulate this amplifier. To simulate this amplifier, everywhere the node DC should be constant. It should not vary. Okay, it should be fixed to some known value. Okay, for that I will apply some simple technique to fix that value. I will discuss in the lab hours. Fine. Anyway, you need to remember whenever you need to connect NMOS and PMOS, we need to connect common mode feedback circuit or some feedback should stabilize the voltage at that node. Is it clear what I'm saying? Okay. Okay, so now come to our inverter, CMOS inverter. You can see NMOS, PMOS. Okay, so in both transistor signal is applied. Okay, so GM1, GM2. Okay, so what is the total transconductance now? What is the total transconductance? Without previously only other stage will be the load. We will take that load resistance. So transconductance due to the input transistor. Now two input transistors. So what is the total transconductance? GM1 plus GM2. Am I right?
Yes, sir.
GM1 plus GM2. What is output resistance? R01 parallel to R02. It is inverting amplifier minor. Is it understandable?
Yes, sir.
Okay. What is the operating region of each transistor? What is operating region? Saturation. You remember? First class I discussed the inverter. Whether I discussed yeah. And we are discussing this amplifier. Both NMOS and PMOS should be in saturation. Digital we studied here and here. Analog we are studying here. Right? Okay. So it's very simple thing. Okay, the next thing is the final thing is with the triode load. Okay, so we already discussed the resistive load. Okay, passive resistor. Instead of using passive resistor, we can use MOS transistor operating in triode region. Right. So what is the triode region resistance? Mu P C R WL since we are using PMOS here. Okay, mu P C R WL VDD VGS minus VTH. So VGS is VDD minus VB VTH. Okay, so we can use triode resistor for the resistive load. The only problem is this triode resistor varying with the process parameter mu P C R and can vary with the threshold voltage. So there is much significant variation will be there. So that's a problem. So it is we need to put some closed loop feedback circuit to make the Rn should be constant. So that's a problem because Rn varying with the device parameters or any other temperature because threshold voltage depend on the temperature, mobility also depends on the temperature. So it will vary with temperature also. So that's the only thing we need to notice. Okay, so that's all about common source amplifier with different loads, diode connector, current source, and triode. Any doubts here?
Sir, in triode load, the voltage gain should be minus GM1 R on 2 parallel R0.
R0 will come. Yeah, definitely.
Yes.
Okay, so definitely come. R12 is much lower. We can take because R0 is a current source impedance. No, am I right?
Yes, sir.
Current source impedance is always higher.
Okay,
Right?
sir.
So we can approximate to R12. Fine.
Okay, sir. Yes, sir.
Okay, so with this thing, I will come to the next topic. The last topic in the common source amplifier. Common source amplifier with source degeneration. Okay, before going to the topic, we will discuss generally how we can write the amplifier gain. Okay, so remember when you discuss the common source amplifier, the gain is minus GM into RD or load resistance or output resistance. So what is RD parallel to R0? Output resistance RD parallel with R0. Right. So any gain we can simply write transconductance into output resistance. What is R out? You can see looking from here. Okay, let me write here so that you can understand better. V in, V out. Okay, so you can see what is the output resistance here, considering both RD parallel R0. So AV equal to minus GM RD parallel to R0. You forget about G negative sign here, but you can see transconductance into R out. So this is R out, output resistance of the amplifier. So R out. What is a transconductance? It is transconductance of the transistor, but I can say it is a circuit transconductance, okay, or amplifier transconductance. It is same as the internal input transistor transconductance. Okay, let's take other example. Let I am taking inverter. Just now we discussed inverter. So what is the gain of the inverter? Let's take here M1, M2. So what is V0? Sorry, what is AV? Just now discuss. What is the
Minus
effective
GM1
transconductance? Minus
GM1 plus GM2
plus into what is output resistance here?
R0 parallel R01 parallel R02.
R01 parallel to R. Right. So now you can see here GM is sum of two input transistors transconductance. So this is a circuit transconductance or effective transconductance. So circuit transconductance. This is output resistance. Okay, so that means looking from here, gain we can simply write transconductance, circuit transconductance or amplifier transconductance into output resistance of the amplifier. Fine. If I want the gain is negative, R out should be negative or GM should be negative. Whether resistance will be negative?
No.
So only possibility is GM. So what is GM?
GM output current by input
Okay, output current
input
by. So
voltage.
let's take small IO by Vn. Here which one
Vn.
can be negative? Input current or voltage? Current. Am I right? Current direction is different. Definitely. So the gain can be defined as inverting or inverting amplifier or non-inverting amplifier, depends on the polarity of GM. Okay, so let's take our here common source amplifier. Okay, so GM is minus GM. Okay, so I will explain how the minus GM comes. Okay, I will explain it later. Okay, so basically you have to understand this. The polarity of the gain defined by the transconductance. If transconductance is positive polarity, the amplifier is a non-inverting amplifier. Okay, it is negative polarity. GM is negative polarity. Amplifier is inverting amplifier. I will tell how that minus is coming. I will explain it later. Before that, we want to know the how to measure the GM. Let's take any amplifier. We are applying the input. We measure the output current. So GM is output current divided by the input voltage, I out by Vn. So how to measure output current? Simply short circuit output. So you can see V0 is there. Okay, so we can simply put short circuit. Short circuit means V naught equal to 0. Okay, so when you put short circuit, you can measure the short circuit output current. So from that, we can write, okay, once you know the I out, we can relate I out by V in equal to GM. So divide by V in, it will give the GM. That means GM is an amplifier transconductor or circuit transconductance, not transistor transconductor. Because you know, in the inverter, it is different. It is not that the circuit transconductance, it is not equal to input transconductance. You can see it is not equal to one single transistor transconductance. Sum of two things. But that's what in looking from gain perspective, the transconductance in the gain term it is called the circuit transconductance. It may be a combination of the input transistors transconductor. Just understand that thing. Similarly, we need to find the R out to find AV equal to minus GM R out. GM we can find by the short circuit current. Okay. R out we can find the output. We apply some AC potential. Find the AC current. Vx by Ix will give the R out. Is it clear? Understandable? And to find the output resistance, we need to make input 0. Fine. We need to apply input 0. That means we need to short the input. Remove the input potential. For measuring the GM, make V naught 0. For measuring the R out, make V in 0. Is it understandable? Shall we proceed? No response. Otherwise, if you any doubt, I can explain once again. Are you comfortable here?
Yes,
People are
sir.
there or not? Boring. People are there. Please respond something.
Sir, it's comfortable, sir.
Yeah. You are not a PG. You are not a UG student. You are PG student. Huh? Please be mature. You cross that age. Don't forget. After 1 or 2 years, you will be becoming a teacher or a professor. And now you are a good professor. You finished BTech student. Now you are engineer. Okay. Don't think like you are a B student till now. Now you can get a job and you can work in some company. That kind of age you are there. So please be communicated. Okay. So now we apply this technique for our common source amplifier. Okay. So you know common source amplifier. This gain formula we already derived. We want to derive this same gain formula, but first we will derive the GM, then we will derive the R out, then do multiply AV equal to GM into R out. Okay. Use the GM formula here. Use the R out formula here, then find the gain. Okay, so first we need to find the GM. So GM, what you have to do? We need to make short circuit, measure the I out flowing outwards. So you can see short circuit output current flowing outwards. Outwards means this direction, not inwards, outwards. Okay, it's very important. Short circuit output current flowing outwards. Okay, this is your definition. Okay, let's take same amplifier. I want to measure GM. Okay, so measure GM and I need to make V out 0, short circuiting here, I out. If V out 0, this is a short circuit. So what is the roll off on the R not RD? Whether it will come into picture? Okay, let me draw again. Some resistance there. I am short circuiting here. Okay, so what is the equivalent impedance here? Here 0. Let's take here some 15K. So what is the equivalent impedance here? 0 parallel with 15K. How much?
0.
Yes, sir.
0. Anything you put short circuit that won't be any effect. Fine. Okay, so it won't any effect here. Okay, so what is I out now? Minus GM into VM. Am I right? Opposite current minus GM into VM. So what is V1? V1 equal to VM. Okay, you can see V1 equal to VM. So what I want to find? I want to find GM equal to I out by V. Okay, so GM to in, so iode by in. So what is effective GM? Minus GM. Now you can see effective GM means circuit transconductance is minus, negative polarity there. So now it is inverting amplifier and non-inverting amplifier. We're looking at the polarity, inverting, because GM comes negative. Right? So ROT you already known. We will make V in equal to 0. So V in equal to 0 means P1 equal to 0. P1 equal to 0 means there is no current source. Okay, so now equal resistance RD parallel to R0. So now I can find GM into R minus GM RD parallel to R. Right. So what do you understand? If GM is negative inverting amplifier, GM is positive non-inverting amplifier. So let me write here. If GM is negative inverting amplifier, similarly GM is positive, the amplifier is non-inverting amplifier. It's very, very important. In future, maybe studying op amp and everywhere. Please, how will you identify the one amplifier for whether it is inverting or non-inverting? You simply apply GM. GM means current flowing outwards. If it is positive, non-inverting. If it is negative, inverting. So this is very, 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 very important. Everywhere it is useful. Because any transistor gain, any amplifier gain can be written GM into RO. If you understand that thing, you can apply this concept of whatever the amplifier it is op amp or whatever may be. Right. So now we'll start common source stage with source degeneration. Okay, so all of you studied about emitter degeneration. Yes.
Yes, sir.
RC, RE, let applying some resistive divided biasing. RB1, RB2. Okay, applying some inputs here. Okay. So it's here. Okay, why you add RE here? Emitter degeneration resistor. What is the purpose you are adding here? Already biasing there. Why you use this thing?
To limit the emitter current.
No. You are correct, but tell in a very clear way. I understood you understood something, but why you use emitter degeneration? As per the bias perspective, I am asking. Already you biased using RB1, RB2. Then why you use RE here? You studied common emitter, it's widely used, common emitter amplifier. You studied BJT, no? In your BTech. Why you use emitter degeneration resistance? It's very important. You studied about, yeah, you just say. Anyone please think and say, why you use emitter degeneration resistance? What is the main purpose?
That to prevent thermal runaway.
Okay. Okay, so let me, no problem. Any other people? You just try, you are from BTech background. Some of you might have gate score. Okay. They might be knowing. No responses. 53 people are there. One of you should know, no? Why you use emitter degeneration resistor? Okay, no problem. I'll tell you. Okay, emitter degeneration resistor we use to stabilize the DC operating point. Okay. So even though we are fixing using RB1, RB2, it could not be stabilized because there is variation due to beta. Beta is not always constant. What is beta? Beta equal to IC divided by IB. Beta is not always constant. IC vary, beta will vary. Okay, so beta is, we cannot understand due to high level, beta is not always constant. The beta behavior is like this. But so you can see we cannot fix somewhere, some variation there, so beta will vary. Okay, so we cannot fix it point. Okay, to fix it here, we can introduce some negative feedback. You can see this showed degeneration, it is a negative feedback. You can see, I'm applying, let's take small signal. I'm applying input is varying. V out will input vary, current will vary. You know, the collected current will vary. That means input is increasing. So what is the equation here? Yes. Collected current will increase. Okay, let me collected current will increase. If collected current increase, what is the voltage across the emitter will increase or decrease? Vin increases. Okay, let me put color. Vin increases. Collected current increases. What is the emitter voltage? V increase or decrease? What is emitter voltage? IE into RE. It will increase or decrease? And then I put in a silent mode.
Increase, sir.
Huh?
It will
Increase or
increase.
decrease?
Increase.
Increase. If VE increases, what about VBE? Okay, let me write. V increases. Collected current increases. Okay, VE increases. If VE increases, what about VBE? VBE is V in
Decreases.
minus VE. So VBE will increase or decrease?
Decreases.
Decreases. If VBE decreases, what about current?
Decreases.
What about current?
Yes.
Huh?
Decreases.
Decrease.
IC
What is the
decreases.
current? IC equal to, what is the relation between emitter bias voltage and base emitter current? E power, let's
E to
take
the power
a small signal perspective. Okay, I'm not large signal. IC is proportional to VB.
VB.
Okay, so current will decrease. So why it is decreasing? Due to negative feedback. Someone increasing, okay, due to this negative feedback, it will reduce the variation. It will stabilize the DC operating point. So this concept due to negative feedback. You study this concept in feedback amplifier. You might have studied in BJT itself. It's a negative feedback. The variation here tracked, okay, tracked by the emitter degeneration resistor. That after tracking it, it will reduce the variation due to VBE effect. Same thing, common source amplifier with the source degeneration. We are connecting in a source terminal. When emitter means BJT means emitter, mass means source. Okay, same thing. Vin increases, the drain current increases. Fine, it will increase the source voltage. Then VGS happens, VG minus VS. It will stabilize the DC operating point. Is it understandable?
Yes, sir.
Good.
Yes, sir.
Because don't forget, even though you can say today every technology mass BJT gone, even though BJT gone, okay, without understanding the BJT, we cannot design, we cannot understand the MOSFET. Okay, BJT is our mother. Okay, we already studied in BTech. Okay, so we should understand BJT, then only we can understand MOS, because something should be basic. We can go to, then only we can go to the advanced concept. But even though BJT gone, people are saying only MOS we are using. Okay, MOS is not completely new. It is coming from BJT only. Right? So modified version of BJT only. Whatever amplifier we are studying, same as BJT only. Only instead of BJT, we are using MOS. Okay, so don't believe BJT can no need to know BJT. No, BJT is our fundamental, our mother. Right? So we need to understand that thing. Only we can understand MOSFET better. Fine. So please, whenever you are writing down, please refer the basics in BJT amplifier, particularly you can refer Siddharth Smith. Right. So Rajavi only MOSFET amplifiers. Okay. Please refer the basic in Siddharth Smith. Okay. So the BJT you can refer the basics there. Fine. Okay. So now we are going to refer common source amplifier with source degeneration. Okay. So this negative feedback thing I already explained. Okay. So now due to this stabilized thing, okay, gain will become much linear. Okay. I will explain how gain will become much linear. That thing I will explain now. But only you need to understand this RS. Okay, we stabilize the DC operating point, so gain will become much linear. Okay, I'll explain how it is become much linear. I will explain in later slides. Okay, so before going to it, okay, now common source amplifier with the source degeneration, how to derive the gain. Okay, first we'll represent small signal without channel in modulation and without body effect. Then we'll go to the, then we'll assume this. First we'll assume simply we'll derive the gain. So this is a small signal. Now we will derive the gain using the general expression GM into R out. Okay, first we will find GM. So GM, what you have to put? V out should be 0. So V out should be 0. What about RD effect? Won't be there. Am I right?
Yes, sir.
Yes, sir.
Okay, so what is I out? Minus GM into V1. Okay, so what is V1 now? You can say now source terminal some resistor there. So what is V1 now?
V in minus
V
Vs.
minus Vs. What is Vs? Okay, let us assume current I out. Same current only will going up because outwards current. Okay, so up here. Okay, what is V out? Minus I out into R because opposite current direction. Okay, so V1 equal to V in minus Vs. Okay, so Vs is minus I out. So minus minus will become plus. V1 equal to V in plus I out R. Is it understandable this expression?
Yes, sir.
Okay, so what you want to find? Minus Gm into V1. Okay, so minus G1 into Vin plus I out RS. From this I can get what is Gm? Gm equal to I out by Vin. So what do you want to get? Gm equal to I out by Vin. So we can find Gm equal to minus Gm divided by 1 plus Gm RS. Is it clear? Now you can see same as inverting amplifier. Okay, without RS, you know the effective Gm was minus Gm. Okay, when I'm adding RS, effective GM is reduced by 1 plus GM RS. Fine. Okay, let me explain the basic here. Okay, I'll put the blue color. I'm applying input here, measuring the output current. Okay, small signal output current, output sorted. So what is GM here? Minus GM. Am I right?
Yes, sir.
Yes. Okay, I'm adding a source degeneration resistor. So what is the effective GM here? Just now we have found minus GM divided by 1 plus GM RS. Fine. So just now we discussed. Okay, RS is a feedback thing. Okay, so you study the feedback thing now. So whenever we are adding the feedback, it is reduced by what factor? Loop gain. Am I right? 1 plus loop gain.
Yes, sir.
Okay, here you can see 1 plus GMRS. So 1 plus loop gain. So in this thing, loop gain is GMRS. So transconductance reduced by 1 plus loop gain. This is due to negative feedback. Is it understandable?
Yes, sir.
Good. We'll more detail more how the GMRS comes in feedback amplifier. We'll discuss. That's very interesting. Right. So please remember, whenever you're adding some feedback here, the whatever the parameters inside the circuit, okay, will be modified by the loop gain. Here modification is reduction. Right. So you might have said in feedback whether input impedance increase or decrease, but how much decrease, the factor decided by the loop gain. Fine. Here transconductance is decreasing by the factor of 1 plus loop gain. Right. So here this thing. So we have derived a GM. Now we'll come to R out. So R out, we externally we need to apply some small signal Vx, okay, then Ix, Okay, then we need to make input 0. So we need to make input 0. Input 0 means V1 equals, okay, sorry, input 0 means what about the V1? V1 will become 0. So this V1 is VGS fine. Okay, so V1 will become 0. I'm sorry, somewhere I'm doing mistake. Just 1 minute, we'll correct it. E equal to 0. So that means it will become shorter. One minute, somewhere in
Sir, it should be RD parallel RS.
this should be grounded. That's what I'm looking how it comes. It should be RD.
Yes, sir. RS is sorted
RS is?
Sorted to ground from here.
That's what how it started to ground. I want to explain it. I want to nullify this effect. So V1 equal to, let me write it, V in minus Vs. It's not a V1. So V1 equal to minus. This should be 0. No, it's intrinsically understandable. There should not be any off here. Yeah. Okay, so let me explain. Think about it. I'll explain it in next class. Okay, I'm sorry. I was having idea. I forgot to mention. No. Okay, but you need to understand R out equal to RD. That means there won't be any effect of RS. Lessness I will tell how. Okay, let me think about it and tell how. Okay, so this is without the channel and modulation and without body effect. That means here you can see body effect is there. I didn't consider it, and we didn't consider channel and modulation resistor. Okay, so now we take into consideration. Okay, maybe this thing I will. Okay, now time 9:50. So with the channel and body effect, I will explain later. Okay, so with this I will finish it. Okay, so now what do you understand? Gm equal to minus Gm divided by 1 plus Gm Rs. So let's take this expression. Gm equal to minus Gm divided by 1 plus Rs. If the loop gain, so just know that gain 1 plus Gm Rs is loop gain. Gm Rs is loop gain. If loop gain is much higher, right? So Gm Rs is loop gain. Much higher. So I can write minus Gm divided by Gm Rs. Right? So Gm will become minus 1 by R. Fine. You can see without a common source amplifier, Gm is minus Gm. With the loop gain, Gm equal to minus 1 by Rs. Fine. So let's apply. I am varying there is some variation in the input. Okay, so in common source amplifier, Gm equal to minus Gm, common source amplifier with the feedback. That means source degeneration. Okay, Gm equal to minus 1 by Rs. Okay, if varying the input, which one is stable? Here or here? Chance, this chance, choice here or choice B? Where Gm will be much constant.
First case.
Huh? Hello.
First case.
Why? Because if Vn is varying, the negative feedback We'll track it, reduce the variation. So GM will become much significantly. That means the variation in GM is much lower. So variation in GM lower, variation in gain also lower. So gain is constant. What about gain here? Vary. Fine.
Yes,
So that's the beauty of source generation. Internal feedback, we reduce the variation. Okay, so that's what you can see. When you plot the GM, it will become 1 by GM is constant. So gain is, now I can say it. Okay, gain is almost linear. It's a weak function of GM. GM means internal transistor GM. Because now GM is minus 1 by RS. So what is GM? GM divided by 1 plus GM RS. So any variation in GM will be cancelled. Finally become RS. So it is a weaker function of GM. Whereas in a common source amplifier, GM is GM. So now we can see strong function. So now here GM effect is cancelled. So weaker function of GM. Is it understandable?
Yes, sir.
Good. Okay, so that's all. The next thing I will with the body effect, that's our channel and molecule. I'll discuss next class. It will take some time. So one thing you want to understand at source generation, okay, GM is become 1 by RS. So gain is almost linear. You can see GM is 1 by RS. What is GM? Dou ID divided by dou V. Since the slope is negative, minus 1 by R. You can see minus 1 by R. I put mod here. It is a mod GM. Okay, but you can take it as modulus of GM. But GM is minus 1 by R. But okay, so that's all about the thing. Okay, so next class I'll finish this common source with the source degeneration. So any doubts here? Varda, are you there?
Yes, sir.
Okay, can you be